Auger Observatory on what we know about high energy hadronic interaction models. It's a pity that I couldn't be there in person, but I'm enjoying very much the conference online, and I want to share with you what we have discovered in the last years on the physics of air showers. So moving forward, I'm going to present the results of the Pierre Observatory. The observatory is now doing 20 years since it started. I think you all probably know the observatory very well. It's composed by 1600 stations of water Cherenkov detectors, and it's overviewed by 4 fluorescence buildings. Here just a very nice picture where you can see the main station of the SD array, and here the fluorescence detectors. And one notable thing about the observatory is that over the years there's more experiments there, and we have these low energy extensions. Namely, we have arrays which are denser, where the grid, instead of having the usual 1.5 kilometers, we have the stations closer at respectively 433 meters and 750 meters. We have buried scintillators that allow us to measure directly muons, to show the electromagnetic component of the shower and to measure directly muons. And we also have some radio arrays that allow us that started as R&D projects and now are progressing to hopefully provide us an electromagnetic energy scale in the future. Finally, we have some elevated fluorescence telescopes that allow us to lower the energy threshold and to see down to 10 to the 17, even lower if you use the Cherenkov light. Now, overall, what we have is this very nice energy spectrum where we can probe cosmic rays above somewhere 5 times 10 to the 16 electron volts up to the highest energies, which allow us to really try to understand what's happening with the ultra energy cosmic rays, particularly with the air shower physics. Now, the great success of the observatory, like Rolf was saying before, for conducting all these sort of measurements, is that it is an hybrid experiment. So it has it can measure showers using the fluorescence detector. So it records the fluorescence light that is produced by the shower when it propagates through the atmosphere. Of course, this only works 15% of the times because we need very dark nights. And we have, of course, the surface detector that is always operating, where we can extract the energy using this reference distance 1,000 meters up from the shower core. The good thing about this is that this was initially built to calibrate our energy estimator for the SD array with the FD array, which provides a quasi-calorimetric energy measurement. But the interesting thing is that we have 2 detectors that can support each other, and we can make a lot of questions on the shower physics. So without further ado, let me move to what we have learned about hadronic interaction models. Now, this is just a short selection, totally biased, of what we know nowadays about air showers from the Auger data. And let me start with the muon puzzle, which is a hot topic discussed previously by Carlos. Now, again, here, what I want to focus is I'm showing you that, of course, there's muon excess, but when you use let's focus on the right plot, when we use ask for the question of the muon scale that you have, and you get the information of the depth of the shower maximum, which is composition sensitive, you can see that even taking into account the very large uncertainties that we have due to our uncertainty on the energy scale, you can see that these are, the data is basically incompatible with all the models. And the same happens when we do the same question but now using, instead of inclined events, we use the buried scintillators, and we still get the same answer. The trick here is that, again, I want to focus on this. We are using an independent energy scale to perform this measurement, so we don't rely on any cosmic ray flats to play with the normalizations. Now we have done more. Over the years, we have collected a lot of data, and now we can do even more. We, instead of just fitting the muon axis, the muon factor that you need to explain the data, we can look into the two-dimensional plots of the X max versus our energy estimator S1000 for hybrid events, and you can sort of have these distributions here. This is the data that we have, about 500 events per beam in theta. And this analysis is conducted between 10 to the 18.5 to 10 to the 19, where we have plenty of hybrid data. And then what you can do is we can extract Monte Carlo templates and try to fit this data using these Monte Carlo templates to see whether we can match them or not. Now, this is very interesting because fitting these two distributions at the same time, if you look at this plot here, you notice that if I move the electromagnetic X max down into the atmosphere, if I make the shower deeper, then I'm moving also the muonic longitudinal profile. This would mean to have more muons. So it's a very important question that we were just recently able to publish and to answer. Now, the result that we obtain, and for me, this is one of the most important results, is that when in this plot, what I'm showing you here is the results of the fits for the different hadronic interaction models. And what you see here is the different tries that we've done with each of these models. And we have done several tries putting our uncertainties, our systematic uncertainties, into these plots to fit these plots. And what we discovered is that regardless of what we consider, we always have a discrepancy. We always found that our data is basically incompatible at a level higher than 5 sigma to these post-LHC hadronic interaction models. So this is a big result and a very statistically significant result. So it's not just a matter of whether we are able to, we see a muon axis or not. The prediction of the models are incompatible with the Auger data, at least the hybrid data. Then what we can do next is to rescale the signal on the ground and produced by hadronic shower at 1000 meters. We call this quantity R hat, and we can try to fit the data. And what we have discovered is that for all the tested models, we see always a deficit in the simulation. So the simulations don't seem to produce enough muons in accordance with what we have published before. Now, the interesting thing for me is that if you look now at these plots, here I'm showing you the X max distribution for the best fit for the different models. And here I'm showing you the signal at the ground, and you can see that the data is sort of displaced. And so this motivated us to play a little bit and to let free one other parameter, which in this case is to allow for an ad hoc shift of the X max. Of course, there's no physics whatsoever on this, but again, it's the idea, it's the muon puzzle still present if we allow for this shift in the X max or not. And when we done this, two astonishing things that happen. So one of those, we get a remarkable agreement between the data and the simulations that you can see here. It's a very good agreement with always very high p-values, except when you go to very inclined showers. Here, the p-value is not fantastic. But the other thing is that we still have this axis of the hadronic signal at the ground, but now the data seems to prefer a shift on the X max. Now, we there are some uncertainties here, some systematic uncertainties, and they are big, but this is not compatible with zero. Now, this is a very curious result, which is not easy to explain, and hopefully it will be extensively discussed in this conference. But I want to show you also a recent paper that was just accepted for PRL and PRD, where we try to extract the Xmax from the SD trace using machine learning methods. For that, we need to deconstruct the data. So this is the footprint that we have, and you need to give it into the network in a way that it can manage it. We need to do the same for the SD traces. And by exploiting these traces and using simulations, we can train the deep neural network to try to extract the depth of the shower maximum. Now, the interesting thing with Auger is, again, we have a fluorescence telescope or detector that we can use to validate, and we have sometimes hybrid events that we can use to validate these sort of black boxes. And this is what we have done here, and you see, so here is what we get by using the neural network, and this is what we get. It's so applying to the neural network to the SD, and this is what you get when you check what is the result on the FT, and you see this striking, very nice correlation. But if you look carefully, you see that also here, it seems that the data is preferring to, we need to do a shift in order to get the Xmax right. So there's a shift for the model used of around 30 grams. Now this is not saying, this is a word of cautions, this is not saying that we should immediately change the Xmax scale. It's saying that when we look at the ground, it's the information that it extracts, and it's trained with the hadronic interaction models, the information that we extract, then if you look to data, we need to shift this information by 30 grams. Then this result is not new, but I think it's very, very important, and it deserves also to be discussed. We have a lot of effort to measure the muon fluctuations, and we did it using inclined showers. This is a very hard measurement, but one that we did it controlling very well our systematic uncertainties. And the result of these relative fluctuations is that it's this one. So you can see it has very large error bars. The data points are basically between proton and iron. But if you plug here the mass composition expectations that you have for when you use our Xmax data, you see that these data points basically agree with what we have. The reason why I think that this is so important is because if you look into what the relative fluctuations are telling us, there's these works that are saying that they are basically connected with what's happening in the first interaction, particularly to what happens, the way that the energy balance is shared between the electromagnetic sector and the hadronic sector. And the reason, if this is consistent with observations of the Xmax, this could be a suggestion that the muon deficit might not be related with what's happening at the highest energies, which would be expected because it's where we don't have any accelerated data, but there might be something that we missed at the lower energies that might explain these results that we're obtaining. So finally, there are many other measurements, and I'm just putting here some of them that we have done over the years. So we have measured the proton-air cross-section, and everything seems to be all good up to 10 to the 18.5. We have measured the shape of the universal shower profile, and again, the models and the data seem to be in the right place. But then whenever we look at the ground, we always find these discrepancies, and this has been reported, for instance, when we look at the so-called delta methods that takes the time information profiles recorded by the SD stations. And you can see this is the mass composition extracted with the fluorescence detector, and this is the mass composition extracted with the SD, and you can see that they don't agree. And more recently, we are working on increasing the number of events that you can get to look into the number of muons, again, we need to have a single at the ground where we count the muons, and we need to have an independent energy scale to do this kind of plots. And this is being currently achieved, and it was presented at the ICRC by using hybrid data combined with the universality method. So what is the future of the observatory? So for me personally, the future is brilliant because it has just underwent a massive upgrade. So now we have just completed it, and we are entering what we call the Auger phase 2 or Auger prime, and we have placed a scintillator on top of the tank, and hopefully this will enable us to measure separately the muon component, the muon shower component and the electromagnetic shower component separately. And so we will have the ability to really test our systematic uncertainties on one hand, and on the other hand, to really improve by a lot the data that we can, because up to now we were basically using inclined events or the MEGA detectors, the buried scintillators. And it's not just this upgrade. There are plenty of experiments in Auger, and I finish with this slide. This is my summary slide. We are entering in a new phase in Auger, a phase where we will be sensitive to, we'll be recording multi-hybrid shower events, and it has proven in the past, it has been proven in the past that whenever you combine two detectors, there's a lot of things that you understand, a lot of discrepancies that emerge. And I really think that in the future we will do much more with the Auger data. And the interesting part is that because we have these low energy extensions, we are covering a very interesting energy, these 10 to the 17 electron volts, which is the equivalent energy to the first interaction with regards to what's happening in a 14 TeV collision, proton-proton collision at the LHC, which is again good news to calibrate the models. And I finish here, and thank you very much.
Okay,